So in this video, I want to talk a little more about clay minerals. And we already know quite a lot about clay minerals. We know it refers to a size fraction in particle size analysis, anything less than 0.002 millimeters in size. We also know that clay and organic matter are part of the colloidal fraction of soils, meaning this is stuff that is so small that it can move around in the pore system. It can be translocated in the soil, as we looked in soil formation. It's part of illuviation in soils. We also know that clays are quite unique when it comes to hydrology of soils. It's got small pore sizes, able to hold on to a lot of water, has a large surface area, has a really low hydraulic conductivity. And we also learned that clay gives rise to plasticity in soils, making it be plastic like Play-Doh. It also gives it cohesive strength, meaning that clay is something that can help facilitate gluing soils together. We've looked at that in terms of how clay plays a role in the aggregation of soils. And we also learned that some clays, not all, have what's called shrink-swell behavior. And that gave rise to one of the 12 soil taxonomy orders, the vertisols, which are characterized by a high percentage of shrink-swell clays. And we also learned that clay is really important for soil chemistry. It has large surface area, tends to have a negative charge, gives rise to the cation exchange capacity, which is really important as a nutrient exchange mechanism. So we also talked about clay minerals when we talked about weathering and the formation of soils. And when we talked about weathering of rocks and parent materials, we noted that oxygen and silicon are the most abundant atoms in the Earth's crust, which explains the great abundance then in silicate minerals. And when we talked about this, we looked at the specific example of a feldspar consisting of oxygen, silicon, aluminum, iron, and maybe some other atoms. And as that weathers, we form a very specific clay mineral called kaolinite, and we also release some of the extra constituents into solution. Now, the feldspar and most other rocks and minerals in the Earth's crust and eventually forming soils are called silicates or aluminosilicates. And with clay minerals, we're talking about a very specific group of these silicates, and they are hydrous aluminum phyllosilicates. The little word hydrous just means that we have water and a hydroxyl, an OH minus involved in there. Aluminum refers to the aluminum silicates, and phyllo, well, that means sheet or leaf. Matter of fact, phyllo comes from the Greek word for leaf. And this is descriptive of clay minerals, not all, but quite a few of them, forming sheet-like structures like you would in a phyllo dough, which is named for the very same reason. So given the abundance of silicon and oxygen, it turns out that the silicon tends to form covalent bonds with oxygen to form tetrahedral structures. You have a silicon in the middle surrounded by 4 oxygen. And these silicon-oxygen tetrahedra that you see here are the basic building blocks of clay minerals. Now the valence of silicon is +4 and that of oxygen is -2. And if you do the math, you find out that each one of these tetrahedron has a net charge of -4. Well, by sharing oxygen with neighboring tetrahedra, some of this extra charge can be neutralized. So here in clay minerals, these tetrahedra form sheets of interconnected 6-member rings of these. And the sketch that you see here is sort of looking down at a planar arrangement of these tetrahedra. And in these, 3 out of the 4 oxygens are shared with other tetrahedra. And that's what makes a aluminosilicate a phyllosilicate. So in quartz, which is not a clay, all oxygen atoms are shared. And the mineral has the familiar formula SiO2. And in a lot of ways, the extent of oxygen sharing is sort of an indication of resistance to weathering. And quartz, as we know, it is extremely resistant to chemical weathering. Well, for these phyllosilicates, it's 3 out of 4s, and these interconnected rings connect each other to other rings via the sharing of the oxygen atom. Okay? So for these tetrahedral sheets, the formula would be Si2O5 minus 2, meaning there's 2 more negative charges which have to be fulfilled somehow. The -2 charge can be fulfilled by combining this tetrahedral sheet with a number of options of octahedral sheets. And here you have an example of an octahedral sheet forming around an aluminum. Sometimes that is a magnesium, but we have 6 oxygen atoms surrounding that aluminum atom. So, and then to complicate matters, it is not just the oxygen being shared, but sometimes these are hydroxyls or these OH minus groups, and combining the tetrahedral sheets and octahedral sheets then forms stable mineral structures. So here's a figure taken from a publication by Christides 2011 that illustrates how these sheets may come together. So we have tetrahedral and octahedral sheets, and in the tetrahedral sheet we have 3 out of 4 oxygens. So these are the white filled circles that are linked together. The remaining oxygen, which is called the apical oxygen, is the one that pairs with the octahedral sheet. And within the octahedral sheet, oxygen and hydroxyls are being linked together. So the example that's shown here in this figure, and I really only included this figure because it's really difficult to draw by hand, is that we have a trioctahedral sheet here. So each one of these hydroxyls connects to 3 octahedral units. Okay? So the anion that would be responsible for forming a trioctahedral sheet would be something that has 2 positive charges, so magnesium or iron. There are also dioctahedral sheets where each hydroxyl connects to only 2 octahedral sheets, and here the anion will be something that has 3 positive charges, so an aluminum. Okay? So the different clay minerals that we observe in nature then simply are a result of variations in how these sheets are assembled, and some variations in the way that these anions are present or missing in there. Okay? So since this figure shows it already, there's also 2 more things to point out here, and that is it shows 1-to-1 and 2-to-1 layers here. And we will discuss those as 2 major groups of clay minerals, 1-to-1 minerals, clay minerals, and 2-to-1 clay minerals. But this will be subject of another video. And then the other thing that's important to point out here, sort of as a look ahead, is also that what happens at the edges of these minerals is just as important as what happens within the minerals and between the minerals. And that is that at the edges, we might have something like a hydrogen bond to a water molecule or hydroxyl happening.